这边被缩小啊。
解锁，请启出话筒。
你讲我吗？room 因为我这边有 breakout room 啊，有，去，还是哦，出了，更奇怪，还是那个哪一个？我们两个一起去剪头发，这样刚好一起剪头发。 No? Okay. Let's start. Okay, maybe briefly go through the concept that we have learned and see how it gets used in derivative. So we learned sup and inf, right? First, using sequence or set. Right? So what's the difference between set and sequence is we enumerate the item. Okay, we enumerate the term in the set. And we form sequence, and what is a sup? So given any epsilon. So if you look at something that less than sup A, epsilon less than sup A, you will find element in A. Okay, it's going to be many of them. Similarly for inf A, okay, so if you look at the positive epsilon distance from inf A, you'll find a lot of item in your sequence or your set. Then we learn limit, right? Okay, limit of AN. So for limit of AN, we have any epsilon strip, we're gonna find all the uh, the term in the tail of your sequence lie inside the epsilon strip for large n, right? Okay, then we learn the continuity. Okay, so now we involve function. And so you take a limit point in your domain, and your function also converge to some point based on the value of your sequence you take. Okay, more importantly, it converges to some other value taken by your function. Okay. And then we can describe it using an uh, epsilon delta definition. So what does it mean here? So it means that in the domain, right, you're no longer looking at limit point, you're looking at some neighborhood, okay, neighborhood around the limit point, okay, some neighborhood, right? Okay, you see here. So you see the x-axis, okay, for the sequential continuity, we consider some convergent sequence, but then in the epsilon delta, we look at some, we call the open set or neighborhood. Then we can replace this FC here. Maybe it doesn't convert to some value of your F, but then it convert to something. Okay, so we'll call it a limit of Fx. Okay, so where we don't really care about the Actual point. What happened at actual point at the limit point? At the actual limit point. Okay, so I purposely vacate that point. Yeah, then you also have epsilon delta condition. Then we replace the sequence using some open neighborhood. Okay. Okay. So then what's differentiability again? So a function f is differentiable if limit of so maybe differentiable at a point if x go to p fx plus so no fx minus fp over x minus p, which we sometimes call it f prime x exists. Okay, so instead of looking the limit of f, but you look at the limit of this gradient here, gradient of the secant with the nearby point. Where the nearby point. Okay, so do you still remember the picture? So I got a function here. E. That's why we look at all the gradient of the nearby secant. Okay, then if you find this derivative, it will result as the gradient of the tangent line at uh, tangent line of the curve. Okay, so actually, secretly, we kind of think of a function from R to R as a curve here. Okay, so when we draw this, we kind of regard this function as some curve. Okay, so this will involve some differential geometry. Okay, good, good. Yeah, right. So we're looking at this particular limit here. Okay, again, it's limit, but then it's a different limit for a given function. So next, let's discuss about the differentiability of inverse function. Okay, so there are actually two ways to think about it. Okay. So actually, there are two ways to think about inverse function. Ways to think inverse function. Okay. One way is this. So say I got this function looking like this. F is y is x. Okay. So do you know how to find the inverse of this function? Rather, what's the definition of inverse function again? You might remember. What's inverse? Okay, what does it mean by inverse maybe? Hmm. Inverse means what? You're going back, right? Okay, so let's say you send x to y. Okay, so how do you go back? I give you y, you need to give me x. Okay, so what does it mean here? So So I have one x, I give you y. Okay, but then if I take y as my domain, I will output x in my codomain. Okay, so you can think of it as swapping the domain and codomain. Okay, so the result of swapping is just this. So you get something like this. Okay, so let's say let me try it. Let me try to do it for you. So let's say this is 2 maybe, and then this is 3. Right. Okay, so then this 2 and 3 point will swap. So maybe this point here become 2, and then this point here will become 3. Like that. Okay. So you simply swap the domain and codomain of F. Or another way is you can flip it. You can flip it. Can you imagine flipping it? Can you imagine? Okay. So doing flipping, right, is actually doing a reflection. Okay, you are actually doing the reflection along the y goes to x-axis. Okay. Yeah. So this is how you get inverse function geometrically or pictorially. Okay. So if we look at the tangent line, right, or the derivative at any point, right, you can see that it also get reflected. Okay, also get reflected. Okay, so we are trying to find the relation between these two. Okay, algebraically. Okay, we're trying to find the relation between these two algebraically. So what do you think? What's the F inverse, the derivative of F inverse? Can I guess? Okay, how does it relate to the original derivative? Okay, so here we come some theorem, which is the inverse function theorem. All right, so if F is a strictly monotone, continuous function on closed interval AB, okay, which is differentiable on open interval AB, then F inverse is differentiable. Okay, at every point y naught of FAFB. Okay, moreover, the derivative of F inverse is pretty nice. Okay, so how nice is it? It's as if the inverse sign and the derivative sign can commute. Okay, can commute. You know what commute means? So it's like this one on this thing here, and then taking inverse commute. Usually we don't have this kind of thing, right? Okay, you don't simply commute. Okay, or in other words, I put like this: 1 over f prime y naught. Okay, let's examine this. Does it make sense to put f prime on y naught? Does it make sense? Where's y naught? Y naught supposedly in the codomain, right? Okay, so instead we should put the pre-image here, pre-image of your y naught. Okay, such that y naught equals to fx naught. Okay, so because you are dividing, right? So you need to make sure that that denominator is non-zero. Okay, so if you look at here, there's a strictly monotone here. Why? So remember last time we introduced strictly monotone for what? Yeah, 1 to 1. And then after that, after 1 to 1, what can we do? We will have a unique pre-image for all the images. Okay, so that we can find the F inverse. Okay, so for the existence for the F inverse. Okay, yeah. Okay, so yeah. Okay, so how do we prove this? So F inverse is continuous. I think this is fine because this is what we did last time. I mean, I showed you last time. So now we need to show it's differentiable. Okay. So basically, if we show this formula here, it implies that it is differentiable because we found the uh, expression for your derivative. Maybe someone can close the door. Okay. Okay. So we're gonna show this formula. Okay, proof. Now suppose that yn converge to y0. Okay. Then we have all the pre-images of these yn and f0 at y0. Okay, so now we want to check what is the limit of the secant here. And we want to check what's the limit of the secant. I mean derivative of the secant. Okay, so basically this is just xn minus xn minus x0 because we are looking at the pre-image. Why is it equal? Because it's unique. Okay, because strictly monotone 1 to 1, we can define a unique inverse. And what is sy not yn minus y0? So we try to relate back to the function f. Okay, because that's the place that we know the derivative happen. But then, can you see here that this is very similar to the derivative of f already? How is it similar? You can flip. Okay, good. You can flip it. Okay, so if you flip it, you just get 1 over fxn minus fx0 over xn minus x0. Okay, so can converge or not this thing? Can can converge? Why can converge? Sorry? No, say. Repeat. I want you to repeat. Huh? All point converge. What do you mean? All point converge? No. Just repeat. It's okay. Repeat. I don't understand. No, it's okay. You need to learn to organize your idea. Uh, uh-huh. To what? 1 point. What point? What point is that? Hmm? What point? Not sure. Okay, does anyone know what point it converge to? Yes. Okay, because f is differentiable. Okay. Okay, so note here that the last term, what's going on? The last term here only converges to the derivative if we have xn converge to x0. Okay, because f is differentiable at x naught. Okay, also provided that this number here is non-zero, so that we can apply limit law, right, to everything. Because to apply limit law to the quotient, you need to measure that the derivative is non-zero. Okay, but then do we have xn converge to s0? What do we assume? We only assume y not go to y0. We didn't really know whether Sn converge to S0 or not. Sn is just some pre-image of Yn. Okay, we are not sure actually. Okay, so we need to prove. Okay, we need to prove. Okay, so since Yn converge to Y0, and so one important thing is F inverse is continuous. Okay, maybe we can try and recall why F inverse is continuous. So what do we need for F inverse to be continuous? Okay, so you need, okay, so you just need your function to be a strictly monotone function that having an interval as a domain. Okay, then it's good already. Okay, so just now we have a function that's on a closed interval. Okay, so we are good. Okay, so then what should we do here? So then y naught converge to y0, what implies that f Sn actually converge to fy naught, but then I can use f inverse because these are the domain. So these points in the domain of f inverse. Okay, so because f inverse is continuous, right? Continuous function will preserve convergent. Okay, so f inverse of fxn also converge to f inverse of y naught. Sorry, x naught. Thank you. Okay, then f inverse of f is just identity. So this will imply that xn will converge to s naught. Okay, which is very nice. Good. Okay. 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 So shit. Okay. Yeah, I think this is good already. Okay. So or in other words, we can just write this as 1 over f prime of f inverse of y naught. Okay. Yeah. Yeah. Any question so far? Or question? Hey, when's your assignment due? This week or next week? Huh? 6月5号 is when? Next week? Huh? Don't have me? Don't have can holiday 6月5号 啊，下周 OK good. This week I think you guys got midterm this week, right? Other midterm. Okay. Maybe we take a break from quiz. So this week no quiz, next week no quiz, then we resume quiz after your assignment. Okay. I think 4. So this is the second last one. Yeah, 4. Yeah. Okay, let's continue. So let's continue with chain rule. Anyone can recall what chain rule is? Chain rule. What's the rule of chain? Sounds weird. Differentiate inner function. Okay, good. Okay, so there's something hiding inside something, right? Okay, so maybe we can get some examples. So anyone can get some high school calculation. Oh, okay, like this one. So maybe we start with Skype's high school example first. Okay, so we want to differentiate this. What do you do? What do you do? Oh, you straight away tell me answer. I tell you, when I teach calculus one, right? No step one, straight away tell me the answer. And then when you ask him, why? I remember the pattern already. Can or Chen Ru also can remember pattern, or Chen Ru also can. I remember the pattern already. 1/2 square root of x plus 1. So got step or not? Also remember pattern already. Any step? Then we can give like next time we give like 3 times chain rule. See you can remember. 3 times chain rule. Okay, so what do you need to do actually here? Okay, so actually there are 2 functions involving, right? So you should like let f(x) equals to square root x, right? And then you should let gx to be x plus 1. There are 2 functions of this kind. Then what is this? This is just f on gx prime, right? Everything. Okay, but then what's the formula for chain rule? So how do you get to this? Should be right, f prime of g of x times g prime of x. Okay, so f prime of g of x, what do you do? What's f prime of g of x? How to read this thing? Well, you should do f prime first, right? Okay, you need to make sure your f is differentiable. So what do you get? 1/2 of square root of x. This one I think you need to memorize. If not, you need to use first principle to calculate it. Okay, but is it hard to do? Maybe we can quickly show this. How about we quickly show this since we have learned first principle? Okay, so f prime of x is lim of, let's say y go to x, square root y minus square root x over y minus x, right? And then you get, you can factorize it, right, the bottom part. And then you can cancel this. Then what do you get? 1 over square root y plus square root x. Okay, but you can see that square root y is a continuous function, right? Okay, so that limit exists. Okay, so square root y go to square root x. So square root x still stay with square root x because it's a limit point. So it's a constant function then. So this will become 1/2 times square root of x. So this is how you get your formula. Okay, so go back and compute your limit of your secant here, gradient of your secant. Okay, so in this case here, what do? You take your f prime x, okay, evaluate. Okay, so this is evaluating at gx. And then times the derivative of x. I think this one's easy, right? So it's just 1. So then you substitute, become 2 times square root of x plus 1 gx. Okay, so you get this. Does that make sense? Okay, good. Okay, so this is what you need to remember from now on. Okay, so maybe in the question, there's no form for you to see already. Okay, so we'll rely on this. Okay, so you need to know how to read this notation here. Okay, so this is not composition, so sometimes you will confuse this, right? Okay, actually, this is not. Okay, this is not meant by this notation. Okay, but then we define f compose x to be fgx. Okay, so this is what we meant by order, This is what we meant by order. This is what we meant by order. The right-hand side is not the left-hand side, but the left-hand side is the right-hand side. So that's why this equal sign is important. We won't write equal here. Okay, we won't write equal here. Because equal should be transitive or symmetry, right? Okay. So we will typically write define. Okay, define meaning we start from the left. Okay, we want to do left, actually we need the right. It's not going right to left. You cannot go backward. Okay. For the right hand side, is just evaluating. You can do it anytime. Any function can do that. Does that make sense? Let me see. Is this equal or not? What do you think? Maybe. Is it always? No way. Why? Okay, sure. But how about this side here? If I restrict to this side, is this always a composition? I think it's always right. This is a function. This is a function. Okay. Right. Then shall we go on? Okay. So let's prove the chain rule. Okay. Let's see. So if f is differentiable at x naught and g is differentiable at fs naught, then gf is differentiable at s naught. Okay, so the formula will be gf prime x naught equals to g prime fx naught prime f prime x naught. Okay, so let's prove this. This proof is somewhat tricky, but then not too hard. Okay, so what do you do? For derivative, well, you straight away go to see the gradient of your secant. So let's consider the limit of this guy. Okay, so this theorem, there's one advantage of this theorem is it tells you what is the form that you're gonna get. Okay, in reality, in research, we typically only know the left hand side. Okay, right hand side here you need to work it out or see a lot of examples. Okay, to guess it. Okay, but then in this kind of lower form course, right, we will straight away tell you the answer already. So actually the theorem is the answer. Okay, but then the proof is to tell me how to get the answer. Okay, so you need to try and relate back to the derivative of f. So you need to somehow create the derivative of f. So what does it mean by creating here? So we can rewrite this quotient to be this. Okay, so if so f converges, so this part will get sorry, f is differentiable, so this part will get the derivative of f. But how about this part here? Okay, we are not sure yet this part converge or not. Okay, I'm not sure yet that part converge. And actually, to make this work, you are worried that actually sometimes whether fx is equals to fx naught. Okay, we are worried about this actually. Okay, so why are we worrying about this? Because okay, we know that this cannot be Sn because this is the point of the limit point becoming a limit point. But to fx naught, you cannot control on, right? Because you just apply f on it. Okay, x xn won't converge to s naught because this is by choice. Okay, but fxn cannot converge to f, cannot be f x0, we cannot control. Okay, so we need to do some trick here. Okay, we need to do some trick here. Okay, here, maybe I make a remark here. Here, x n that converge to s naught, we have Sn not equals to x naught by choice or by construction. But we are not sure about fxn converge to xn such that fxn not equals to fxn. Okay, we are not sure about that. So instead of looking at this quotient directly, so we're gonna introduce some special function. So to prevent fx minus fx naught to be 0, okay, for some f x naught, we're gonna introduce an auxiliary function. Okay, h. Okay, so h of let me see here. From the domain of G, okay, to R. So let's do this. So here, so we're gonna send y to gy minus gfx naught over y minus fx naught if y is not fx naught, and then we sure we'll send it to g prime of f naught, g prime apply on fx naught if y equals to fx naught. Okay. So why can I do this? Okay, so why can I do this? So actually, if y is not fx naught, we just keep it as a quotient form. If it is, then we replace it. Sure, we'll replace it with the derivative there. Okay. Why can we do this? Because g, we know that g is differentiable there. Okay, so there is a value there. Okay, so instead of so in this setting, what do we do here? What have we done here? Okay, so if y is not fx naught, we will look at the gradient of that secant. If it is, just replace with the actual derivative there. Okay, let's see how this this h will help us to find the g. Okay, let's see how it helps. The derivative of g, or the limit of gf. Okay, the limit of gradient of gf. Okay, so since g is differentiable at fx naught. Okay, so h is actually continuous. Okay, continuous at fx naught. Okay, so do you know what to check here to check this is continuous? Okay, so really, what you need to do is to check at this point here, because we want to check at continuous at fs naught, right? But then to check continuous at fs naught means what? Left and right limit should be the same, right? Okay, the limit from the left or from anywhere is converging to this point. But then we set it as the uh, gradient of the secant of the nearby point. Okay, so it's definitely continuous here. Okay. So then what can we do here? We can compose it with fx, sorry, f log. Okay, so we can replace this with fx. Okay, for some fx. So here inside here becomes fx. Here becomes fx. Right. Maybe I keep the original form first. So here will become fx. Here will become fx. Okay. So this is the this quotient that I'm interested in. Okay, after composing. Then what? Then what we have done is, so maybe now it'll be clearer why I do this. So then for gf prime x minus gf x naught over x minus x naught will be equals to h of fx times fx minus fx naught over x minus x naught. Okay, so why is it equal? Okay, it is equal if definitely when fx not equals to fx naught, but even if fx equals to fx naught, what will happen? Okay, what will happen here? Both sides will be 0. No. Okay. So what have we done here? What have we done here? This is a technical point actually. So if you're gonna split your quotient like this, right? So there's a technical point here. So here is the technical point. So you need to address this technical point here. Okay, so how do we avoid this technical point here? So instead of looking at this splitting, okay, we directly look at this function here. Okay, so meaning we don't want the form of this splitting. Instead, we want this piecewise thing. Does it make sense? Okay, so it's like previously you were just playing around with the expression, right? But then now to go around with this technicality, we define it piecewisely instead. Does it make sense? Okay, so at that special point there, the special point that can make this derivative 0, we replace it. Okay, replace it with another point. Okay, that makes sense. Okay, so in this case here, if you just replace x with x0, right, then this term is immediately 0 over something non-zero. Because this we can make sure that xn is not x0. On the other side, we also have this property here. Does it make sense? Okay, because hf of s0, we get this special point here. Okay, which is non-zero. Or which is 0 also doesn't matter. Is it okay? as long as we don't have the 0 occurring in the denominator. This is our point. Does it make sense? Okay 吗？有问题吗？ Okay, but then if this happens, right, how does this converge? Huh? Okay, so how does this converge when x go to s naught? Okay, we know that hash f will converge to Sn, to Sn will converge to S naught, and then the other side, because f is converging, because I mean the gradient of secant of f is converging because f is differentiable, then altogether we'll get g prime f x naught on f prime x naught. Okay, does it make sense? Okay, ma. Any question? Uh, okay, any question? No? Okay. So instead of dealing with this fraction directly, right? So we're gonna define some piecewise function, okay, to take care of the special point there. Okay, that could make your denominator 0. Okay, but then it still works. Work as a function. Okay. So there are two forms of gfx minus gf x naught over x minus x naught, but we prefer the version of h. Good. Okay. If no question, let's take a break. Okay, let's break until 10:56. We'll start the attendance. You can try and log in. 啊，改完了。Yeah, yeah. 你们几时要讨论？这个星期？这个拜三放假，我没有在。拜四啊，你们拜四就要讨论啊？嘿呀，那是要看的是啊？什么？不想看？讨论 final 啊？呃，average 啊，忘记了。But then 我觉得比我以前的还比较好一点呢。以前是比较，想想有没有差？啊，哦，因为有时候老师教顺序有差别，而且呀啊对对对对对，不同老师有时候他的速度会不一样，然后重点有时候也会不一样，其实教慢点。 夕阳又在睡觉了。你快点想，呀，吃饭了，还有没有钱？嘿，嘿，
因为我现在还在 integrity 的课，所以我可能上这一班，然后我再就过去了。
所以你现在是过去年是？
就过下里 integrity 啊，因为那边有课嘛。
OK，可以。
然后这个拜四我可能会缺席，因为我有考试
啊。OK，过后啊，
就你要
准备年考。
对，因为好像是3点多到5点上个时间。
OK。
我发现到我们是一题被玩的。
真的咩？
我是来玩的。我第一题我把那个题只是 the subset of empty set。
The subset of empty set is empty set。
可是真正其实是 the set of all subset of empty set 这句是什么？
我觉得你刚才讲的那两个东西是一样的哦。
他没有讲到
The set of all subset 啊，the subset of 那个也是，它是全部连它。
可是刚才讲的是 all subset of
all subset。可是我们在讲 all subset of empty set is empty set 的时候，我们就把那个 subset 当成一个全部的 subset 当成一个 set。
是啊，可是题目是the set of all subset。
所以意思就是
那个 set 里面有empty set 的 subset。
对，没有错。可是你刚才讲的 subset of empty set 也是这个意思啊，也是这个意思啊。The subsets of the empty set。如果你要讲 is an empty set 的
多少？
那个 now set 吧，因为它的
不是，是你要注意那个题目，不是 the set of the set of。可是，
那你们会记住那个题目吗？
我脑翻，就突然间想起来。
没有，因为你在讲 is empty set 的时候，就是你把前面那个东西要当成一个 set 来看。
对，只是把 subset 当成一个 set 来看。
subset。看你怎样写吧。你有时候你会写的 subsets 加 s 嘛，就是它的那些 subset。
讲the subset of。
对，那这个就是 set of all subset。
好像是这样子。
呀，不然怎样呢？
不是只讲这个 subset。
如果你要讲其中一个 subset 的话，我们会讲subset 哦，一个 subset 哦。如果你是指那些所有的那些 subset 的话，应该通常是写那些所有的。 不然的话你就会讲subset 哦。subset 就是那个
对题目是
题目是他们讲的 the set of all，所以我没有 ambiguity 那边，我就直接
我就看出题目，然后所以
哦
我就把这句话我理解的是 subset。
然后那个 reason 是什么？那个 reason
就是那个
是
题
false reason，
里面有一个东西啊，
有一个
就是 null set 嘛。
啊是啊，
一头脑，
里面的那个东西是 empty set，太多 empty set 了。
第一题就是骗子，A 坑人一个加可能，以为是 B 是 continuity，然后
哎，第二是 D 那
layman's terms continuity is when you can draw the graph with a pencil，
人家是在班上
using the
讲废话
pencil。
讲不是吧？我们东西不讲，为什
对
么不知道？
对，有 example，
后面这个就是来哦，后面这个就是来。我上次我记得还有讲
啊什么
就是他讲过，就算我
hint 的意义
就是给你
啊
recall
就是说就是平时人家说你要画那个continuous graph，你不可以断嘛，对不对？反正我们有一种是无限断的，你断到很密的那种，
那个 evaluation
啊，对，
这个是我错了。
exactly 啊，I think 有2-3个写出来了，
写出来，
把那个function写出来。
这方式嘛 ，f iteration 呢 ，x 嘛，差不多。
对，对，它分开 define rational iteration，
最难的是第7集这个，
最难的第7题。
是吧？
哎，对，没有错。但是 B 跟 C supposedly 不会难的，A 是最难的。
第一个谁去背那个复杂的 trust？
那个 A 啊，是吧？我没有证明哦，可是我直接用你的那个 A 的那个 statement 来证明。
可以啊，那个就是它的意义来的。你 A 做不出，你 B 和 C 还可以做出来，你只要用 A 的结合。C 也是可以。
C 是什么
？every continuous。
哦 ，every continuous。
然后我也是喜欢。他们就对，好，这个在 A 方面，
是对吧？
是的呀，啊。Okay, then we will move on to Extremum. Okay, so a very standard treatment here. So Extremum. Do you need to recall how to find Extremum? Also calculus one stuff.
find local.
Good. Okay, yeah. Okay, sure. So depend on you want to find local max or absolute max. Okay, so these two things will map precise here. And then we will differentiate these two things. Okay.
我现在就明白了，为什么 extreme 一定是这4个 point 的其中
4个 point 是哪4个？
是那个 local maximum 还有 absolute maximum。
Yeah, now we're gonna do this theory in detail. Yeah, we're gonna do this in detail. Sure. Yeah, we're gonna address the question. Okay, so where we only care about stationary points and so on and so forth. But then we need to define the maximum minimum properly first. Okay, so there are 2 kinds of things. One thing is you are a absolute maximum. Okay, you are the highest of all. Okay, no one is greater than you. Okay, so this is the absolute max. If fx greater or equals to fy. Okay, so when we say x is the maximum point of f, so this x here live inside the domain of f. So actually we compare the value of f. Okay, I'm the f. So for all y in here, or what should I say? Or equivalently, we already learned the soup language, right? So fx should be the soup of among all the fy, where y is in df. Okay, so here, what do I say here? So because soup of a set, right? It's just a number. Okay, it's just a number, but then we want it to be f of something, which is fx. Okay, f of something. Okay, it's achieved by my f. I can get the suit one. Does it make sense? Okay. Similarly, you can define a minimum. Okay, x is a minimum point if fx less than or equals to fy. Okay, for all y in, yeah. Okay, so or equivalently, fx is equals to the inf, okay, of the set here. Okay, next is about a local max and local min. Later we'll draw a picture to distinguish these things. So local min, local max first. Okay. So what's local max first? So local max point of f if there exists an r greater than 0 such that fx greater than or equals to fy for every y just in the open neighborhood of x. So x minus r up to x plus r. Okay. You can imagine this r can be small. Okay, so it's just locally. So let's say if you are badminton, your badminton very cheap, right? So you are, how good are you? Maybe you are good in Muar only, local max. But you are not good in Malaysia, okay, in the whole country. Okay, you are not the absolute maximum. For example, Lee Chong Wei is the best in Malaysia, right? But then you go out, lose to Ling Dan again. So it's not a low absolute max. Okay, I'm just giving a point of view. Okay, so people might think that he's the best, right? Yeah, but I mean, I just give you a point of view. Yeah, yeah. 我故意在马来西亚讲，要意识到自己的不好。对，没有啊，他们有退休前我也是在讲。Okay, anyway, so alright, local max, local min. Okay, then we can apply local min as well. Okay, so basically you just copy paste this whole thing here. So copy paste this. Okay, so we can change it to min. So how to change it to min? So here min. So we just simply swap the inequality. Okay, so maybe I give you a picture. Maybe picture like this. Ooh, 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 like that. So maybe I pick some point here. A, B, C, D, E, F. Maybe here, G. Okay. Tell me which one is a local max, local min, and which one is max min? Huh? ACE. What happened to ACE? Huh? Huh? Local max. Okay, because you have some open neighborhood around it to make it a maximum. F can be local max or not? I think sometimes depend on how we treat this endpoint here lah. But then you can see that for this definition, the right hand side doesn't exist, so we won't treat it as a local max. So sometimes we call this a boundary point. So sometimes when you check local max minimum, right, you need to check on boundary point, because at those point, sometimes derivative doesn't make sense. We didn't define one-sided. Depend on how we treat. That's the theory. Okay, sometimes we define one-sided derivative. If you realize the definition of our derivative, right, we care about point from left, right. Okay, so unless you have a one-sided derivative, right. So these are local max. Then you know that these are also local mins, right? Okay. And then the max and min is on the other side. F is the maximum, G is a minimum. Because you compare with all the points in your domain. Okay. Quite good, I think your concept. Okay, any question? No. So the maximum or minimum point, we call it extrema. Minimum local max or local min, we call it local extrema. Let's see. Okay. Maybe we introduce one useful limit definition, okay, for us to prove things easily. So we will define a one-sided limit. So sided. Okay, instead of going left and right arbitrarily, we're gonna do consistently left from left or from right. Well, so how do we define it? Well, let's do this. So we can define f we say f tends to the, so let's say fx tends to the limit L as x tends to C from the right. Okay, so this one is from the right side. If, okay, for every epsilon greater than 0, there exists a delta greater than 0, such that if, okay, x minus C is greater than 0 and less than delta, then we have the usual epsilon convergence here. Okay, so you can see that I remove the absolute value on x minus C. Okay. Well, so is it clear that this inequality gives you right hand side or not? The point on the right hand side. Huh? S minus C greater than 0 means what? Where is S? Where is C? S minus C greater than 0. So X should be greater than C. Okay, so it's on the right hand side. Okay, so if left hand side, then what should you do? Good. So that's the left hand side. Okay, so here we will write it as, so we say that, so in this case, we will say that lim x to C plus of fx equals to L, like that. Okay, so this is what we mean using epsilon delta. Okay, so similarly, one can define the right hand limit. So lim of x go to C minus fx equals to L, like that. Okay, I think you learned in the calculus, right? Lim of x go to C, you get L if and only if the left limit and right limit also converge to the same thing. Okay, I mean, like, one side should be easy, right? One way of the proof. What do you think? Which way is easier? Which one is easier? Left to right easier or right to left easier? Huh? Left to right. Why? Huh? Left to right is easier. Why? Why? Huh? Why? Wait. Why? Left to right is easier. Why? Then what do you think? You have to make decision. There's one way is easier. Think about the definition again. Okay. So one of this delta work for what? This delta work for the absolute value, right? X minus C greater than 0. Delta. And then this one is what? One of them is S minus C. The other is C minus X. Okay. So if you have a delta that work for both sides, right? Definitely use the same delta on this two side, right? Does it make sense? Correct or not? So this will all definitely work for x minus c and c minus x, right? Because absolute value. Okay, but then on the other side, if you have convergence, okay, for delta 1, convergence for delta 2, right? How do you make the convergence for the original f? How small you need to make so that left right can bound by delta? How? If you got the left side convergent, you got the right side convergent, how do you make sure left and right converge together? Max, max, the largest one. If the max one, let's say this one is 2 lah. This one is 4 lah. Okay, I choose 4. Then how do you make sure that the left one converges? Because the left one only converges when your delta less than 2. You understand what I say? Yeah, minimum. Okay, so from the right to left, you need to pick delta to be the minimum of these two. Okay, from the left to right, you just take delta 1 equals delta 2 equals to delta. Okay. Make sense? Okay. Okay, so once you have this delta, your epsilon convergence will follow. Okay, good. Okay, so this is what it means by left right equal, then you get the limit of your original function. Okay, so now we're gonna prove this local extreme theorem, which sometimes we call the Fermat's theorem. Okay, so this theorem didn't say that, or if this happen, this is the local maximum. Instead, it do the other way around. So it do the other way around. It says that if f has a local extreme value at, let's say, c, and moreover, if f is differentiable at c, then f prime c is 0. So maybe I want to talk about the significance of this theorem first before I prove it. So just now, when I tell you the local extreme point, right? What did I tell you? You just go and compare your f value. But then here, it relates it to differentiability. Okay, it relates to differentiability. So not every function you can do this, you know. For example, last time I told you the absolute value, right? Function. This minimum here, you cannot find it using a derivative. Okay, you need to go and compare all the value. But if you have differentiability, then you can try and get this condition here. Okay. Does it make sense? Okay. So maybe you might ask, how one thinks about this derivative? Why can we make extreme point to derivative? What do you think? What do you think? Why can? Think again. Just now I told you what derivative means. What? The tangent, right? Gradient of the tangent, right? And then this local extreme value point says what? You are the maximum or minimum around a neighborhood. Okay, so the picture looks like what? There are two kinds of picture, right? Either look like this, your neighborhood, or either look like this. What do you mean 0? Why gradient is 0? Why? Tangent line is what? Horizontal. Okay, because it's horizontal here. Okay, you need to somehow pass through a horizontal line, which gives you the gradient 0. Why? Because you need to go up on one side, right? Definitely you need to go down. So when you go up and go down, definitely you need to go through some horizontal plane. Does it make sense? Or you go down, you have to go up, right? Then you have to like go through one horizontal place before you go up. So this is the point of this local extreme theorem. But I didn't say that if your horizontal, I mean, if your tangent line is horizontal, then that must be a local max or minimum. It doesn't say that. Okay, but this gives a necessary condition. Okay, but necessary condition is good enough already. Meaning what? If you are local extreme value point, right, your derivative have to be 0. So meaning what? You can go and find this derivative point to be 0 first, and then you filter them. You filter them whether they are local max or minimum using comparison. Okay. Usually, sometimes we prefer sufficient condition because sufficient condition will tell us how to find them. Okay, but then here you need to extra job. So if I just give you a necessary condition, then it might be some other point that is not a local maximum, but the derivative there is still 0. Okay, you need to remove those points. But this is already clear. Okay. Good. So let's prove this. Not too hard as well. So we're gonna use the power of the left-right limit to do this. So we're gonna split it to left and right. So suppose that f has a local max. Let's see. Okay, so minimum is the same, so we will keep it. So there exists a R in R such that for all x in A, B, if the absolute value of x minus c is less than R, then fx less than equals to fc. Okay, well, so what should we do here? So not that. For the left-hand side of C, fx minus fc over x minus c should be greater or equal to 0. Okay, can we verify this? Can verify this? Fx minus fc is positive or negative? Because fc is a local max, right? Fx smaller than fc. 没有错啊 because fc is a local max, right? Fc should be greater or equal to fx.
Then why is it?
Yeah, so that's what I'm asking here. So this one give you what? Fx minus fc should be less than or equal to 0, right? But then this give you what? X minus c should be less than or equal to 0. So you divide something less than or equal to 0, so you invert. Equal 可能还是不可能？属于 equal 不可能。S 减 C 哦，这个不可能，上面可能，下面不可能。OK， 就算不可能，我也可以这样写，你知道吗 ？Why? Because this is more, this is an all statement. Okay, yeah. 有些我是这样，是这样真的，我的老师这样跟我讲啊，我教我的 analysis 老师这样，周末你可以写小于等于等于不对也不用紧。False 吗 ？True or false 还 still true 吗？对不对 ？But then 如果 if you want to be precise 啦，就 throw away 了，比较好了。不对的东西就不要写了，意思这样。齐安看，齐安是 double standard 的，齐安 double standard。他如果他自己错 imply 对他讲可以写哦，就是逻辑对哦，人家错 imply 对，不可以，那个不可以，要写错了那个。double standard 齐安，他没有来我们大讲的，没有。他这样，他在我也是这样。OK。Okay. Right. So this is for left hand side, lah. Okay. How about right hand side? For x is in C to C plus R, then the inequality will revert. Okay. Okay. But then what do we know? What do we know about this function f here? What do we know? This function is differentiable. Okay, meaning what? These two number, I mean, if you take limit, they have to be the same. But what sort of value you could take there? What are the intersection number between these two range here? One has to be less than or equal to 0, the other is have to be greater or equal to 0. So if they have to coincide, what should their limit be? And the limit of this thing have to be must coincide. I think this relate to exercise that Haoran did in our tutorial, right? Yeah. So you cannot converge to something strictly positive than 0, and you cannot converge to something strictly negative to 0. Okay, because on one side, you need to always stay above. So maybe let me draw it first. So on one side, you need to strictly stay above on the non-negative side. The other side, you need to strictly stay on the non-positive side. So if they converge, they only can converge to this middle thing. Okay, because you can use contradiction. Let's say if you want to converge to something at the bottom, then here there's no one staying inside here. Okay, there's nothing from the positive, non-negative side staying at the negative region. And then if you try to converge to something strictly positive, okay, there's no one from the other side that's gonna stay on the positive side. Okay, yeah. Okay, so the only place they can converge together is 0. Okay, they both can get very close to 0. Okay, so that is f prime c equals to the lim of fc x going to c of fx minus fc of x minus c, which is equals to the lim of x going to the right side from the right side. At the same time, is equals to the limit going from the left side, okay, which is 0. Okay. So how do we find the number 0 here? Because we argue that the left and right limit have to be the same, and then if they have to be the same, the only possibility they can converge together is the point 0. Okay, they cannot converge to other point. Okay, using contradiction. Okay, it's the exercise that Haran did. I posted up in the Moodle also. Then the picture I think tutorial 5. You can go and try and see. Any question so far? Okay, so you can see that you can see that how when we explain using picture and then how we explain using this analysis here. Okay, try and see what's the similarity and what's the similarity and what is the difference, okay, in the argument. Okay. Actually quite similar, right? In this analysis here, we also say that on the left hand side it should be looking something like this. Okay, on the right hand side it should be looking something like this. But then pictorially I told you that if you want to move from here to here, then you need to go through some horizontal point. But then the analysis use the limit to tell you left and right limit have to exist. Okay, so they have to exist. So meaning they have to meet somewhere. Okay, the way that the place that meet is gonna be the horizontal line, like that. Does it make sense? Okay. So you need to learn both language here. Okay, one language you need to show to mathematician, the other language you can show to any lay person or any newbies. Yeah, in particular, when you teach first year, maybe they look at this, they headache. Okay, but if you look at this, they can play around with it, right? They can play around with this line here, straight line. Then you can move the straight line, and then you can see that, oh, it really passed through a horizontal, which give you a gradient 0. Okay, so maybe some remark I want to make here or warning. So this doesn't work if your local extreme value theorem happen at the place where it is not differentiable. So meaning these are the singular point sometimes we call, okay. So these point you need to check separately whether they are local extreme value or not. Extrema. And the converse of this is not true. Okay, so the converse of this is not true. Can you think of an example where you have a 0, yeah, but every point is a local max and there, right? At local max and local min at the same time. Yeah, constant function is very weird, huh? You can be a local max and local min at the same time because we just require less than or equal to, right? Equal is fine. Yeah, what example you can think of? I think you also see in calculus one. Yeah. Yeah. Anything you can recall? There's a thing called inflection point, right? If you remember inflection point. The first place you see inflection point is where? Fx equals to? Yeah, s cubed. Okay, so you can analyze the changes of your tangent line. So you see your tangent line is like this, and then go straight and then go up. But then if you check here, right, this is f prime 0 equals 0, right? But then is this a maximum or minimum? Local maximum. Okay, so around it, you can see that there's some point higher than it. The other side, there's some point lower than it as well. Okay, so it cannot be either both lower or highest, lowest or highest. Okay, yeah. No matter how small your interval can get, no matter how small, you cannot find a neighborhood. Okay, such that either it is the highest or either it is the lowest. Okay, you cannot find. Okay, no matter how close it is. Also, local extreme value theorem make no sense on local extreme that occurs at the endpoint. Okay, it seems like we accept that it can occur at the endpoint. Let's see. Okay, right. Okay, there's a remark that actually this local extreme, right, can occur at the endpoint. Okay, at the endpoint. Maybe we should take this into account. We allowed endpoint here. Why? Because let me see. Where's my definition? Okay, maybe we should allow these into our local extreme definition. So, maybe let me say why. Okay, maybe let me say why can we allow it. Okay, so if you examine this definition here, the interval here, Okay, so let's say if at the endpoint, right, if it is at the endpoint, maybe let's write this into x minus r to x union. Okay, x to should we include x? Let me think. Depend on what endpoint you get, right? Either you are closed or you are open. Let's consider the open case. Then if this doesn't exist, right, then this part should be empty. Okay, so I think should work, should still satisfy this condition here. It's still a subset, right? So you have a non-empty set union, an empty set is a subset of something. Because empty set is always a subset of any set. Okay, so I think we will include, so here we'll include endpoint case. Yes. Good. But then in this case, I think we didn't do one-sided derivative in this course yet. I think we didn't do that. So we don't discuss derivative at the endpoint. We assume there is no derivative there. Yeah. Actually, if you want to do one-sided, also makes sense, right? You get what I say? Because you are just considering the limit of the gradient nearby, right? So you can like form this gradient line, and then you find this gradient. But then we cannot extend this definition, you know. We cannot extend this because if you imagine we can try and extend this graph, right? So it might be the case that we extend this graph such that this derivative doesn't make sense anymore because left and right is not the same already. Okay, so depend on what you want to do, actually. There are books that define one-sided derivative. And then say that left and right derivative have to be the same so that this is differentiable. Yeah, you can do that. But then we are not doing that. So we will say that the endpoint is not differentiable. Okay, not differentiable for the endpoint. So you cannot find derivative there for now, for this course. Is it okay? Yeah. So endpoint, no need to talk about derivative. Okay. When you want to talk about derivative, make sure you can go from left and right. Neighborhood. Okay. But maximum minimum can because we are just comparing function. But you can imagine that if I extend this function somehow, it will not becoming a local max anymore also. Yeah. So depend on convention actually. Okay, depend on how we're gonna discuss these things. Okay, these are all the possible way we can. Yeah. So but then maybe in this course we include endpoint. Yeah, include endpoint. I think calculus 1 also we did that last time in the BSc one. All right, so let's do next corollary, which is the first derivative test. So we'll say that let f be continuous on the closed interval AB and differentiable, okay, on the open interval. So here we throw away the endpoints. Okay, we throw away the endpoints. Then the extrema of x. So this is an absolute extrema, not the local one. Occur on the closed interval AB. Can occur where? Can either occur at the endpoint or at the point where the first derivative is 0. Okay or not? Okay. Yeah. So if you want to be a local max, you need to be, the derivative should be 0. But then you can find your extrema from this local max. Okay, so this theorem says what? Our first derivative test. So if you want to find the extrema, right? For example, this picture, right? Where do you find the extrema? So one of them is you go endpoint and check which one is larger. The other is go to find other local maximum. So you compare all these A, C, E, F. Which one is the largest one? Okay. First you go and find the endpoint. Okay. Second, you go and find all the local extrema. Because the point where you get derivative 0, right? Either is a local maximum, either is nothing. Okay. Then you compare all these. So let's see which one is the largest. Okay. Good. Good. So this is first derivative test. But then there's another way, right? If you don't want to compare this value, do you still remember from calculus 1 what do you do after you differentiate once, or your high school also teach you, right? 没有咩？忘记了。You differentiate once, right? You get the stationary point. Then how do you find maximum minimum? Then Differentiate again, right? Second derivative. You look at the second derivative. If it's less than 0, it's maximum. Greater than 0 is minimum. So you differentiate second time, second derivative. Yeah. If it's less than 0, then it is a maximum. If it's a greater, then 你怎样确定谁是最大呢？你一个一个检查。什么？你这样找最大的？对啊，是咯。我不觉得我们以前会做这样的事情哦。我们接 second derivative 啊。Yeah. Right. So that later we'll prove that our second derivative test. Okay, but for now it's just comparing. Okay, for now it's just comparing. Later we'll prove second derivative test also. That's the another way. That one need to rely on your f prime is differentiable. So you need to make sure your f is twice differentiable. You can do that. Otherwise you cannot. Okay. Even for this first derivative test, you need to make sure your function is differentiable. Once differentiable. Okay, so for this test is quite limited. But then for our usual daily purpose should work. Okay, but before that, I think we need to prove some cool theorem first, which is Rolle's theorem. Rolle's theorem. Yeah, Rolle's is another mathematician, so you can try and do research on him. Again, same condition. Let f be continuous or not. I think just define is enough. Just define a, b, and differentiable from the open interval a, b. Okay, if f a equals to f b, then there exists some point in your domain a, b, such that f prime c equals to 0. Okay, you know how to think about this? How? That's the picture I drew before. Yeah, good, very good. So which one? This one? First two, right? Okay, so if your endpoint is the same, right, maybe this one is FFA, and then this one is BFB, such that FA equals to FB, right? If your function is differentiable, then there should be some point in middle here that have a derivative 0. Okay, some point. It doesn't say 1 point, 2 point, 3 point, it can be multiple point. So you can imagine something like this. Okay, you can imagine something like this. So you can imagine something like this. Whoa, like that. Okay. Does it make sense? So then you can have a multiple point that have 0 derivative tangent line. Okay. Does it make sense? Okay. So from this result, what can you think about differentiable function here? What do you think about differentiable function here? It can be just straight line also can. Okay, it can also be just straight line, constant function also can. If it's constant, then it's easy. It's always derivative 0 at any point inside there. But then if it's not constant, then what are you going to do? Well, if it's not constant, what are you going to do? So if it's not constant, and you need to somehow get some theorem to tell you that this function can actually go up, go down, so that we can use this the first derivative test, right? I mean some result of first derivative test. Okay, to tell you that. Okay, so proof. If f is constant, then just consider any Okay, any C in AB. Okay, just consider any C in AB. Now you will get F prime C to be 0. Just take any one of them. Okay, suppose it is non-zero. If F is non-zero, what does it mean? I mean non-constant. It means that it will have maximum and minimum. Okay, because it's defined on the closed bounded interval, which is differentiable on the open interval. So by extreme value theorem, there will be some maximum and minimum. Okay, so if it has a maximum minimum, right, what could happen? What could happen? So maybe let me draw some cases. Maybe FA here, FB here. So maybe the max and min is higher and lower than it. Right. Or maybe all these are minimum and then local max maybe go up a bit. So I shouldn't draw here. Or what else could happen? Or maybe these 2 points are already local max. And then local min is lower. Okay, but in all cases, right, what can we deduce? In all cases, we can deduce that either max or min, or actually both, yeah, either one of them will work already, of f on the interval AB is different from FA equals to FB. Okay, from these two numbers. So what? But this doesn't matter, right? So as long as the extrema occur, where do I find the zero derivative point? It is exactly on this extrema. Okay, this extrema will give me the first zero first derivative. This will give then just give f prime c be 0. Okay, by again extreme local. Wait, why I got two different name one? What do I call it? Oh, local extreme value theorem. Wait, extreme value theorem. Let me think. Extreme value theorem. Hey, this extreme value theorems is what we did a long time before, right? Where did we did it? Yes. So if you have a function defined on a closed bounded interval, right, you will have a maximum minimum, right? I think this is a result of the yes. And also this is a result of the Bolzano or thing, right? Yeah. Otherwise you cannot find that point. You need to find that special point, the intermediate value point, or you need to find the sub min point. These need those theorem. Okay, good. So, but how to give this f prime c to be 0? You need the local extreme value theorem that we just proved just now. Okay, let's call it LET. Okay, local extreme value. Okay, good. Okay, so the picture, maybe some generic picture could look like this. Or some generic picture maybe could look like this. So maybe you could have this kind of case, or maybe you can have a different case, like this case. Yes. Okay. Yeah. These are the C between this A, B here. Okay. These cases correspond to what I draw here. Make sense? That correspond to what I draw. So you can like this, okay, or you go like this, or you go like this. Okay, the generalization of Rolle's theorem is this. Okay, maybe once we do this, we can go back home. Which is the famous mean value theorem. Did calculus 1 do mean value theorem? How do you think about mean value theorem? You serious? You guys did Rolle's? Let me think. I think I also did Rolle's in calculus 1. Okay. Sure. Okay, so let f be continuous on closed interval AB and differentiable on open interval AB. Then there is a C in AB such that f prime C equals to FB minus FA over B. Okay. So what does this mean here? Can you like see this in a picture form? Okay, so you should draw your function again. Typical differentiable function is like can draw the function without lifting your curve, right? Lifting your hand. So maybe draw something like this. So you need to take your endpoint, your A and B, right? Okay. So what's the right-hand side expression there? It is the gradient that connects the point AFA and BFB. So meaning this line here, the gradient of this line. Okay. What does it say? It says that this is achieved by some other gradient. C. C is in between AB. Is it true? Okay, so let's copy it. Can you find other point that also have this gradient line or not? I mean, tangent line with this gradient. I claim that there's at least two for those for the graph I draw. So one of them is here. Okay, the other one is here. Special, no? Special, huh? Okay, but this one is just a picture. But then I told you that there's some wave function maybe could occur, right? Okay, so how do you prove it in general? So this comes from Rolle's theorem. Did you realize how it came from Rolle's theorem? I'm not sure anyone told you about this trick or not, but I'm gonna perform a magic to you. Because it didn't say that whether FA is equal to FB or not, right? But then we can always do this though. Rotation. Okay, Rolle's theorem. Proven. Proved by rotation. Proved by rotation. Okay. Yeah, it's not the same, make it the same. But then this is also what the proof do, you know? This is also what the proof do. Let me show you the proof. Although we didn't say rotation, but then do you know how to make two numbers the same? You take difference, right? Yeah, so this is exactly how we prove this generalized mean value theorem also. Let me show you the proof. Yeah. Okay, so you see, so instead of looking at F, okay, what we did is we're looking at this H here. Okay, we look at this H here. So this H here is actually Fx taking away what? Taking away the how do we call this thing? Let me think. How do I motivate you here? How do you interpret this? You take your fx and then take away the value. Okay, let's draw this, see how I motivate this actually. Okay, so let's say you got this graph, right? Also FA is something here, right? Okay, so in this case, if you look at what's this? If you look at H apply on A, what do you get? You get FA exactly. Correct or not? Oh no, wait. What do you get? HA you get 0? Is that true? HB you also get 0. Ah, let's see. Okay, so I think what this guy is trying to do is he gonna shift this function down to 0 first. Okay, and then for the other point, how do you treat them? You take your fx and then you go and find the tangent line. Okay, so what you do is you wait. So let me draw this gradient first, this part of gradient. So this part of gradient, let's draw it using this. So you get this tangent line, okay? And then what you do is you push this tangent line, you push this gradient to this x minus a. Where's x minus a then? Let me think. I'll try to think about this x minus a. Oh, okay. So I guess you do this and then minus a. Minus a means you minus a means what? Okay, 我现在在讲什么 Okay, so I'm trying to figure out this point here. So how to think about this point? Okay, so I already settled fx minus fa, right? So this means you will shift your function down by yes. Yeah, you can. Okay. But then 你还要解个 fa 哦。是吗？哦，你也可以这样想，我觉得你也可以这样想。OK，啊，减
就是它的 endpoint 上去变，就是拉去零，
拉去零，
就是y 坐标 endpoint 的 y 坐标拉去零。
OK，and then
然后就可以来一个。
怎么 FB 会拉到零那边呢？
对啊，
你说说看。
但是要画一下。
要画，肯定要画。我现在就是在想讲话，我现在就是一直在想讲话。要画我要画，你来画，来，我有3分钟，来你画一下，
还是画，
你画，
还是画在这里吧。
这个这么大个不够大，
可以也可以拉新的页。
啊，可以啦，一定做给你，
可以。
我们服务很好。
OK， 我假设，对，这里标两个点，我这个是 BF of B，
是，
我这个是 AF of A，
是，
然后过后假设表现这个
OK，
这个就是它的 secant line， 然后过后，因为你看 secant line 它的这个 endpoint 啊，跟那个 f of x 的这个 endpoint 是一样的，所以减了过后，它就会拉到这个是你的那个新的这个 function 的这个
没有错，
就是 h of a 哦，我这个就是 h of b 哦。
Why h of b 会跑去那边？
因为他们一样。f of b 等于f of b 等于这个在 b point 的。
Okay. Maybe we should see this then. So, it means that it means that your f value need to take away the distance here. Okay, so I think I found the distance already. So for AF of A, the distance here you need to deduct. And then for BF of B, the distance here need to deduct is this. Okay. And then for the rest, you need to use this to deduct. Okay. So then in this case here, what happened here? So so for this part here, right? Let's draw the new one. So here. So the new one will be something like this, right? Okay, but then how about this part here? 好像会跑到这样是吧？会这样。Yeah. So how? 也是下去？我想一下，会对吗？对。后面还是下去啊，只是做一个 shifting。Let me think 啊，对啊，就是 shifting 吧 ，I guess。Is it? Not exactly shift, right? 我想一下会发生什么事情。Anyone can imagine what happened here? Let's say 剪掉差不多这样子，有显示啊。Do you keep the shape or not? Do you keep the
他们就是两个点他们之间的那个vertical distance 就一直增加然后在减少
vertical distance 一直增加，然后再减少。对。什么 ？Sorry? What do you mean?
Why we use the second line
to
differentiate this?
Uh-huh.
The second line is constant, and what we get is hx prime equals to f.
No, I want to show it in the graph. I don't know what you mean by no need. I don't know. Yeah. Okay, maybe what I want to discuss is this compared to the rotation that I mentioned just now. Actually, it's not quite rotation, because if it's rotation, right, you can see this point here is becoming here. But then if you just take the difference, right, it is not actually. So it is like it's like you still keep the general shape, because if you do rotation, right, your local minimum could change. But not if you do rotation. So I wouldn't say it's a rotation now. It is just some difference. Yeah, you just take some difference such that your two endpoints have the same value. Because if you do rotation, you see your minimum could change, your maximum could change. Okay, but then if you just take the usual difference, right, the minimum and maximum place didn't change. Does it make sense? Okay, ma. So there's a slight difference as taking rotation and this one. This is my point. Okay. But then the idea is the same. The idea is the same. Okay, maybe if you want to do rotation, maybe you need to somehow shift this local max and min back. Yeah. But then if you just consider topologically, that's fine actually. Yeah. I mean, if okay, never mind. Ignore my comment just now. Yeah. Okay. So if you do rotation, the local max and minimum will change. Okay, but then if you just do the differences that we did just now, the local max and minimum should be the same. Should be the same? Yeah, should be the same. Because you are taking linear difference, right? So the linear difference should keep your inequality the same. Okay. So far, so good. But any comment? Huh? What? 下次再说 OK 好，下次再说可以没问题。好 OK then in this case here if you try to compute the h prime c it is exactly the f prime c. Okay. Oh sorry, f prime c minus fb minus fa over b minus a. Is it correct? Okay. Is this inequality make sense or not? Does inequality make sense? Let me think. Okay, maybe we left these two next time. Okay, so we'll continue with this again. Okay, continue with this again. Yeah, continue with this mean value. Okay, so we'll break and see you next Thursday. Wednesday is a holiday, by the way. So we'll see you on Thursday.